Well, welcome. Today is Wednesday, March the 10th. We're hump day, making it through another shortened week because of e-learning and the ACT. Talking about acids and bases. So we're kind of going through the notes that are posted online. And so kind of going through here and looking at our definitions of acids and bases. On the first page of the notes, it just kind of gives us definitions. And we're just looking at conjugate acids and bases. But I just wanted to point out this one, this PO4. What would be the acid, the straight up acid with PO4? H3PO4, because it's a -3. So we're going to put 3 hydrogens on it, be H3PO4. And so if this is the phosphate ion, what would be the name of H3PO4? Phosphic or phosphoric acid. Okay? Is that a strong or a weak acid? So H3PO4 is a weak acid. Now, as we lose each successive hydrogen, what does that mean about the strength of the acid? Do they get stronger or weaker as you lose hydrogen?
Stronger.
They become more negative, and remember, it's harder to take the hydrogen, the H plus, away from something that's now negative. Okay? So we look at our Kas of H3PO4, and if you look up here, you can find H3PO4, first column, about 2/3 of the way down. Its Ka is 7.5 times 10 to the -3. Then you go to the top third, H2PO4, it's 6.23 times 10 to the -8. Then you come down almost to the bottom, HPO4 is 2.2 times 10 to the -13. So as Ka gets smaller, what does that mean about the strength of the acid? It's getting weaker. What does that mean about the strength of the conjugate base? Stronger. So if I'm looking at PO4 3-, that's the conjugate, not of H3PO4, because there's always one hydrogen at a time. It's the conjugate of HPO4, this one. Okay, these two are conjugates. We're going the opposite direction. This is going to be a very, very strong base, because this is a very, very weak acid. Okay, which means that the reaction is going to really, okay, it's going to go this way. It's going to make this doesn't want to be like this. This has a super strong attraction, so it's going to want to get that hydrogen. This is going to be a strong base. This is going to continue to react with water and go back up and make H2PO4. And so, conjugate acids and bases. Strong acids make weak conjugate bases. Weak acids make strong conjugate bases. It's always the opposite. All right, that's all just review. Continuing on. I mentioned this, I can't remember if I mentioned it in your class or not though. What does the amphi prefix mean? Like an amphibian. Be both water and land, right? So what do you think amphiprotic or amphoteric means?
Both acid and base.
Molecules are how you can read well. They can be an acid or a base, depending upon what you put them in. And water, we're seeing water as amphoteric. In that, if you put an acid into water, water acts like a base. You put a base into water, it acts like an acid. So it depends upon what you put it into. Most amphoteric substances are fairly weak acids or bases. And again, up here, if you look at any of your hydrogen anions, like hydrogen carbonate, that has a hydrogen it can donate, become like an acid and go to CO3 2-. But because it's negative, it can also accept a hydrogen and go to H2CO3. That's why that bicarbonate, baking soda, and even the fizz and pop, that when you dissolve carbon dioxide in water, you get some of that bicarbonate. It helps settle your stomach if you have an upset stomach, because it tends to help get the pH right, because it'll buffer. We're going to learn later on in this unit about buffers, and we'll read how the blood has a bicarbonate buffer in it to keep the pH somewhere right between 7.2 and 7.4, because you get out of that range, your organs begin to shut down. And so we have to kind of keep, you got to kind of keep it, right in that pH. Okay? So, just if you see that something is amphoteric, I use the word amphoteric, not amphiprotic. just means it can act like an acid or a base depending upon what it's in, okay? Now, we don't, all the answers to those are down there, so you can look those up and just kind of go over there. Then we talked about the relative strengths of acids and bases, okay? Strong acids, what do we know about ionization with a strong acid? 100%, that's kind of what that's showing. HA on the left, before and after, it's all H plus and A minus. That's your 100% ionization. But a weak acid, generally less than 1%, so you start with HA, you put it into water, most of it stays as HA, and you just get a little small fraction of H plus and A minus. So strong acids give a high concentration of H plus, a weak acid gives a low concentration of H plus. That's just kind of a little structural. And looky here, these aren't even my notes. Strong acids, memorize these 6, okay? That is going to be on our stuff to memorize list. Those 6 strong acids, okay? Notice the bond strength between the H and the F is the strongest, and so as a result, HF is considered a weak acid, not a strong acid. It's not one of the 6. And it has to do with that strength of that bond. So what type of acid would we call these? They only got 2 elements. What'd you say?
Binary.
Those are the binary acids. Okay, and remember the strength of the binary acid is number 1 based on size, because the bigger it is, the weaker the bond, the easier the hydrogen is to get donated. So HI is the most easily broken bond, weakest bond energy. As a result, it's the strongest acid. And then HBr, then HCl, HF is the weakest of the hydrogen halides, and so it's actually classified as a weak acid due to bond strength. I don't know why they put the bottle of hydrochloric acid on there. Then we talked about what determines whether an acid is going to be strong or weak, okay? And we had, for oxyacids, we had 2 factors. What were the 2 factors? The oxygen to hydrogen ratio and electronegativity of the non-metal that the hydrogen and really what the oxygen's attached to. So here, we can just kind of look at this table. HClO4 is super large, somewhere 10 to the 7th, okay, but it's really approaching infinity because it's almost 100%, okay? 10 to the 7th is what, 100 million, 10 million? 10 million. 10 to the 6th is a million. 10 to the 7th would be 10 million. Okay, so that's the value of K. All right, the amount of product of a reactant. HClO3, some consider this still to be a strong acid, but it's not ever one of the 6. So it's approximately 1. Then we start going down, HClO2, the Kas get smaller. And then H2SO4, it's a 2 to 4 ratio. It's large, but H2SO3 is not as large, so it's that hydrogen to oxygen ratio. And then we look at the electronegativity. If I was to compare HOBr, so how do I say it? HBrO4, would that be stronger or weaker than HClO4? Weaker, because the halogens, the electronegativity decreases going down. Remember we talked about it being an electron withdrawing. So the more electron withdrawing, the more the electrons are all pulled this way, the stronger the acid. Okay, so you should be given a list and be able to identify which one's the strongest acid based on just structure. And we did several practice of those in the back of your book on Friday. Okay, and then this here, the stronger the acid, the weaker its conjugate base. We already talked about that. All right, we're getting to the end of what we've come across. Okay, the vast majority of acids or bases are weak. Okay, we already know that. We only have the 6 strong acids, and we have our 7 strong bases that make the block B on the periodic table. All right, that's all good. And so that simply means the Ka is going to be much. What is this thing? Two less thans. It's much less than. When you put 2 like that, it means not just a little bit less than, much less than. Okay, just a little math notation there for you. That's very common. Okay, but we already kind of know that the value of the Ka, it's products over reactants, and so the smaller Ka is, the fewer products there are, the weaker the acid's going to be. Now, weak bases, I don't think we talked about those at all yet. Weak bases are very difficult to recognize. The reason why a weak base is hard to recognize is because it doesn't have OH in it. It reacts, fancy word, it hydrolyzes the water. In other words, it breaks the water molecule apart. So when I'm looking right here at this ammonia, ammonia is the most common weak base. And notice again, by the 3 definitions, we're producing the OH minus. So it's a base by whose definition? Arrhenius. Okay? The water is donating a hydrogen to the ammonia. Right? So that makes this a proton donor, which is a Bronsted-Lowry acid. This is an Arrhenius acid. Definition. Okay? But according to Lewis, what's happening? Lewis is saying that the electrons are being donated to the hydrogen, and so therefore this is a Lewis base. This is a Lewis acid. But in terms of weak bases, you're going to see that anything that has a lone pair of electrons like this, if it can accept a hydrogen, it's going to, from the water, if it can break the water apart, it's going to produce the hydroxide. So turn to the back of your book to page 1104. We've been there before.
Like actually, Mr. Collins,
Huh?
how did they come up with all of these?
What do you mean come up with all
All
that?
the K values.
Somebody is just looking, I mean, they can, how well something conducts electricity, it tells us how many ions are present.
Okay.
And so they're probably just measuring the electrical conductivity of the solutions and figuring out how many ions are present and going from there. Probably some government-funded job somewhere. Some government seems to be funding everything these days. All right. What common element, besides carbon and hydrogen and all of these things, what common elements there? Nitrogen. From biology, these NH2 groups are all called amines, okay? Dimethylamine, ethylamine, hydrazine, hydroxylamine, methylamine, okay? An amine is that NH2 group. Every single one of these has a lone pair of electrons on the nitrogen. This one has 2 of them. Okay, this is gonna be dibasic. This can handle getting 2. Now this is just for it to gain 1, but it could gain 2. It could put another, go to N2H6 2 plus. Okay? It's going to be this, even though we have an OH here, it's the nitrogen that's gonna be the donator of the electrons. And in each case, if you combine any of these with water, H plus, OH minus, it's going to that lone pair. So we're going to end up getting the conjugate after this accepts. This is a base. You make NH4 plus, the ammonium ion, and OH minus. Here, aniline, you're going to go C6H5NH3 plus. You're adding an H plus each time. And this is ammonium. This is going to be the anilinium ion when it makes that plus. Okay? And then we have, this is going to be CH32NH2 plus. So each one's going to gain an H plus. It's always going to be on the nitrogen. Now, it's pretty obvious when I'm pointing it out like this, but when you're doing a problem and you don't know if it's an acid-base problem or not, and you're just trying to figure it out, it's sometimes hard to recognize that that's a weak base, because it just doesn't have anything that says base in it. So we have to be, this nitrogen, this amine group, always acts like a weak base. Another clue that this substance is going to act like a base is they will give you values of Kb. What does that B stand for?
Base.
Base. If they give you the Kb, it's probably going to be acting like a base. And bases accept hydrogens. So just see what would be made. And you have to have a lone pair of electrons for that hydrogen H plus to go to. Okay, so it's going to go to the thing that has the lone pair. Generally, almost always, for a weak base, it's going to be a nitrogen. At least in this class. We good with that? So, many of these, kind of goofy looking. If you go look at the bottom of the notes then, right there on that page, a lot of the common, those ones that I just gave to you are written down here. These are some of your common weak bases. So if you want to write that in on your notes, these are just those common weak bases. Notice they all have the nitrogen on them. So that's generally everything that we've talked about so far with acids and bases in a 30-minute review. Probably 25 because of the time taking to set up the video. Does anybody have any question about any of that part? Do you feel like you can recognize acid and base? You know understand the 3 definitions? Okay, we can do conjugate acids and base, conjugate acid-base pairs. We understand how to be able to tell the relative strengths of acids based upon whether they're binary or oxyacids and the oxygen to hydrogen ratios and those things. And now we can look and recognize what a weak base is going to look like. Acids are easy because even weak acids are easy because they still have the hydrogen out in front. It's just going to be a matter of how much it ionizes. But weak bases, we just have to look for that amine group. All right, so let's look. Today, the rest of today is about equilibrium constant. Okay? Kb for a weak base is much, much less than 1. And there is some more values for those. That's the same thing as page 1104. All right. So, what would be the equation for ammonia in water? And bases, by the way, because the OH is gonna come from the water on a weak base, you have to include the water in the equation. So does anybody even remember what ammonia is? What's the formula? NH3. And we add water. Now this is when I write water as an HOH. What are we gonna get? NH4 plus OH minus. Right? So what's my KB gonna be? KB is K, just like any other. Right? And if you look up on a chart, you'll find that that KB value is 1.8 times 10 to the minus 5. Turns out acetic acid is the most common weak acid. Its Ka is 1.8 times 10 to the minus 5. Ammonia is the most common weak base, and its Kb is 1.8 times 10 to the minus 5. I don't know how or why that works out that way. It's just one of those miracles of nature and science. Ka and Kb expressions look very similar. It's the hydroxide ion versus the H3O plus ion. But again, it's still products over reactants. More than one's product favored, less than one is reactant favored. All right, so let's look at doing a Ka, or pardon me, a Kb problem. Actually, let's do this one first. Okay, 14.2 is on the previous page of your notes. That's just your Kas. Now, are any of these acids? Water can be either one, right? Okay. What acid did this come from? HF, right? What's the Ka of HF? You need one of these. You need one of these. All right. Then HCl. HCl we know is just large. HNO2. What's the Ka?
4.0 times 10 to the
And then HCN.
6.2 times 10 to the 10.
Okay, so excluding water, of these four, which is the weakest acid? HCN, right? So what does that mean about the CN minus being conjugate?
Strongest vein.
It's the strongest conjugate base, right? So I look at the acid from which it came, the value of the Ka, the stronger the acid, the weaker the conjugate's going to be. So which one's the next weakest? Okay? I would say that that number is bigger than that number. Is it not? They're both 10 to the minus 4, but 7 is bigger than 4. So that means that this number is smaller than that number, so that makes this one my next weakest acid, so therefore what's that NO2 minus is the next strongest base. So we're gonna go CN minus is greater than NO2 minus, which is greater than F minus, which is greater than Cl minus. Now, I was leaving that one off just because the water auto-ionizes. What does it mean, auto-ionizes? It does it by itself, okay? H2O plus H2O goes to H3O plus OH minus. But this Kw is equal to which is 1 times 10 to the minus 14th. So, what did they say? According to their strength, they doing this the opposite way of which I'm doing it, but the H3O plus concentration here is equal to 1 times 10 to the minus 7. OH minus is equal to 1 times 10 to the minus 7. So the H3O plus is the part, well actually it's the OH minus that's going to act like the base. So it's 1 times 10 to the minus 7, so where does it fit in this? It's going to be, when we look here, 10 to the minus 7 is 10 to the minus 10. It would be right here, to me, it'd be right between the Cn minus and the NO2. They have it over there after the Cl minus, but I'm going to count it as the 10 to the minus 7th in here. So it's going to be, that's where it's going to be. I'm never going to ask you about the water being, because it can go either way. This part is what I'm most interested in for you guys. So what's the concept there that I'm bringing across? What concept am I trying to get you to take away from me? What about conjugate acids and bases? Okay, the weaker the acid, the stronger the conjugate base. And we can use the Ka's to determine the strength of the acids. The smaller the Ka, the weaker the acid, which means the stronger the conjugate base is going to be. Is that making sense? All right, we need to do some math. We need to get your brains working. But I just wanted to kind of walk you through those notes to show you that, what page, that's page 7. And page 8 is the auto-ionization of water, which we just really had already talked about. Page 9 is the pH scale. I am assuming that you guys can already do all of these. If you don't know how to do all of this, you might want to practice it. The answers are always given here. And so that's just, again, these are, if you know what the, concentrations are, you just take the negative log and the negative log, and I'm assuming you can all do that. We talked about that on Friday. But this is where we're going to keep going, calculating the pH of a weak acid. This is where we started. But when we get, here's your ice table. What can we assume about this X? Okay? Now, on this particular one, 1 times 10 to the minus 4th and 1 times 10 to the minus 1.8 times 10 to the minus 5th is not big enough difference to make the exception on the X. And so they go through and say you can cross multiply, get your quadratic equation, and then put it in your graphing calculator. You're never going to have to do that. Ever. Ever, ever. Okay, so don't even worry about that. So you can almost scratch that part out if you want to. This is going to be more realistic. This next page. Okay? So we're just showing here, we can neglect the X and it just comes down and shows at the bottom that you get basically the exact same thing. Okay, so that's just saying, this is just a justification of why we can negate the x in that equation. All right, so I'm gonna let you keep going. See, look at it, we're on page 13. This is why I really want us to spend the rest of the day kind of going through these problems. Okay? The hypochlorite ion is a strong oxidizing agent often found in household bleaches and disinfectants. Also, I can create the forms when swimming pool water is treated with chlorine. So in other words, you're swimming in Clorox. In addition to its oxidizing ability, the hypochlorite has a relatively high affinity for protons. What does that mean, high affinity for protons?
It's a shell
Affinity for protons means simple what? What does affinity mean?
Electron withdrawing.
Not electron withdrawing. If the electron affinity was, what do we do with electrons and electron affinity? It's the love for electrons, it's an added force. So a strong attraction force. So it has a high attraction for protons. What does that make it? A base. It's a much stronger base than Cl minus, for example. It forms weakly acidic hypochlorous acid. Calculate the pH. So all of that is fluff. Here's the problem. Calculate the pH of a 0.1 molar aqueous solution of hypochlorous acid given its Ka right here. So let me see you do that in your notes right there. That's a review from Friday. So go back and look at those notes if you're a little bit rusty. I keep saying Friday because I feel like yesterday was a Saturday. I think I did all this on Monday. Okay, this should be a relatively straightforward problem. We can go directly to a shortcut. But if I have my ice table, what's my change gonna be? Minus x, plus x, plus x. So I'm at 0.1 minus x, and x. So I'm at x times x. Well, what can I do with x on the bottom? Assume it's negligible, so you can go straight to h plus equaling the square root of 0.1 times 0.1 times 3.5 times 10 to the minus 8. That's your Ka. That's what you're going to end up at every time. Now, all I'm doing is here, I'm multiplying this, get x squared is equal to this times this, then take the square root to get x, which is my h plus. And what does that come out to? Okay? So how do I find pH? Just take the negative log of that. And it turns out to equal 2.3. Okay, so when you just have a straight weak acid, we find the pH, you can go straight to this equation right there. It's got to get to that every time. Now, the rule again is that this number has to be 1,000 times greater than your initial concentration. This one is way more than 1,000. This one's 10 to the 7th times bigger. Okay, so if you plugged in, if you wanted just to kind of prove it, you have your fancy calculator, and you just plugged in this equation like this, you would see that that's going to come out probably to 2 sig figs, exactly the same number. Okay, now if you don't want to make the assumption, you can use your fancy calculator and do all the math. But this is the first time sig figs that you're printing. All right? Now, I'm just going to touch on this next one. We got a whole bunch of problems coming through here, and that's what we're going to do the rest of the period. I'm just going to work through this one quickly. We have two acids, Ka of 10 to the minus 4th and a Ka of 10 to the minus 10th. Somebody read that out loud for me. What's that say? Amar, what's that say?
On the top,
Yeah.
only the acid with the largest Ka value contribute an appreciable H plus. Determine the pH based on this acid, ignore any others.
Okay? 10 to the minus 4th versus 10 to the minus 10th. This one's going to produce a whole heck of a lot more H plus than that one. So we just ignore that one. We just find the pH of this one. So we can just say that my H plus is going to equal the square root of 1 molar, no, 5 molar. Times 4.0 times 10 to the minus 4th. And somebody give me a value for that. See, with a weak acid, you can go just straight to that equation.
0.045.
0.045,
Yes, sir.
and then take the negative log of that.
1.35.
Okay? So this problem is really identical to the other one, but this is what's important right here on this. Okay? got this? That's important. All right, now, then it says also calculate the concentration of the cyanide ion. So HCN, well, HCN is going to break apart very little, but it's going to do this. So I know that my Ka of HCN is 6.2 times 10 to the minus 10th is going to equal my H plus times my Cl minus all over HCN, okay? But this time the H plus, we're in a mixture, the H plus is going to be that concentration. So it's kind of like a common ion problem now. Because we have H plus coming from this and H plus coming from this. So I just plug that in and I say 0.045 times X, and then this is going to be the 1 minus X, but we're going to negate the X. So then it's just going to be 6.2 times 1 divided by 0.045. I bet it comes out to 1.4 times 10 to the minus 8.
Yeah.
Okay. I have not really hardly ever seen a problem like this on AP. It's just kind of good to know. This could be bonus type question. Okay. Just a mixture. The biggest thing is in a mixture, if you have one that's strong and the other one's weak, you just ignore the weak. And when we get into acid-base neutralizations and looking at graphs and pH at the end of the titration, that'll kind of come into play again, but just more in a qualitative manner. All right, good stuff. But you have all this study material. So now, how do we do this? Percent dissociation. What's percent? Part of the whole. What's the whole going to be on A? 1 molar, right? So this is going to go HC2H3O2. It's acetic acid. It's going to break up into H plus C2H3O2 minus, right? So percent dissociation is going to equal what over what? No.
The equilibrium value of the.
What's percent? We just said, what, you just told me percent
It might
is,
just be the
well, first off, what's percent?
part of.
Part of the whole. What did we just say the whole was? 1 molar. Just the H plus concentration. Because for every one of these, you're going to get one of those. This is just telling how many of these, for every one of these, one of those broke apart, dissociated. And it's really, we need to change this to the word ionization. Covalent compounds don't dissociate. It's the percent ionization. No. Very semantic, very technical, but. So how do I find my H plus? Well, we can go straight to square root of 1 times 1.8 times 10 to the minus 5. Times 10 to the minus third, okay? So, 4 point, well, we can do the math pretty easily because we're dividing by 1, right? So therefore, the percent ionization is going to be 4.42%. Not very much. But if we do the same thing on B, square root, 0.1 times 1.8 times 10 to the minus 5. Now it's going to be the square root of 1 times 1.8 times 10 to the minus 6.
1.34 times 6.
So now my percent dissociation is going to equal 1.34. Well, I don't even have to do the math on that. Again, oh no, it's divided by 0.1. So that's going to, what is that, 10 to the minus 1, I'm going to subtract minus 3, so 1.34 times 10 to the minus 2, so 1.34%. So what happened to my percent ionization? It increased, right? Now, did my pH, do I have more H plus in solution? No. I have less H plus, but a greater percent ionized. The more dilute solution, the more waters there are to go around to pull the ions apart. Okay, so the more dilute the solution, the greater the percent ionization. That doesn't mean the pH is going to be lower, stronger acid. It just means that you have a greater percentage. That's going to be true when you're dissolving anything. The percent, when things are dissolving, the percent ionized, especially like KSP problems, it's always going to add water. It's going to favor production of more moles of ions. Okay? It's always going to go to the side with more dissolved ions. So, I don't know what you want to write on the side in here to make sure you remember that. But the more dilute, the greater the percent ionization. The reason why this is confusing is because the percent ionization is greater, but the pH is still higher. It's still not as strong of an acid. So obviously a 1 molar acetic acid is a stronger acid than 0.1. But percentage-wise, more of the molecules break apart in the 0.1. Lots of stuff to kind of process with acids and bases, which is why I like to keep it to the end, because then it hopefully stays a little bit more fresh with you as we get closer to the AP test. Normally, I would, again, have already done oxidation and reduction reactions and been through with that, but I'm going to try and get through as much as I can of acids and bases in these 2 weeks before spring break. Touch up any loose ends, spend a week or so in electrochemistry, and then spend the rest of the time reviewing. All right. Look at that, page 15 already. Let's go the other way. Let me see, you guys are going to get to do this one. Remember, in our equilibrium problems, we had 3 different ways in which we could calculate the K. You could be given the concentrations directly, or you could be given an equilibrium concentration, which would be pH of the solution. Or we can go with, there's a certain percent that reacted. This is like that exact same problem, just percent reacted. All right, we should be finished. What's my change gonna be here? How do I find the change? Anyone?
0.1 times 0.096, I
No. How much is dissociated? 3.7%. So how do I find what that is?
Multiply by
0.1 times 0.037, which is going to equal 0.0037, correct?
Mhm.
So it's going to be minus 0.0037 plus 0.0037 plus 0.0037. So this, if I have to find Ka, I must know all three of these values. So it's going to equal 0.0037 squared divided by, don't make the assumption here, go ahead and subtract it out, and we're going to end up getting 0.9963, 0.09963, 0.0963. And that turns out to equal 1.4 times 10 minus 4 to 2 sig figs. And this is my sig fig limiter right there. bases, when I do want to find the same type of problems with a base. Well, before we even go to there, I think we already did this type of problem. I think we did this exact problem. Okay? We can find Ka if we're given the pH, right? How do we do that? We did,
You take the,
Hey, that's like when you and Miss Love.
what?
You and Miss the share.
No,
I can't remember, did we do these problems or not here? I think I did them in 6th and 7th period, but I don't know if we did these problems here. Okay? Well, let's do this phenylacetic acid. It's one of the substances that accumulates in the blood of people with phenylketonuria, an inherited disorder that can cause mental retardation or even death. And if you look on a bottle of Coke Zero, you will find that it has that phenylacetic acid in it. And it has a warning on there for people with this. Okay? Because if you drink that, it's going to have a negative effect on you here. Okay? So, a 0.85 molar solution of this has a pH of 2.68. And the reason why I want to stress this, and you can kind of put this right in that same section on your notes, even on the back of the next sheet or whatever, because this kind of relates to the same thing of a weak acid. There's several different ways, we can, given the Ka, we can find the pH, but if we have the pH, calculate Ka. So Ka, now, y'all, I don't want to write all that out. I do know that this is the H that's ionizable. It's the one that's separated out. It's the COOH. It's that carboxylic acid. Okay? So I'm just going to say HX. So it's going to be H plus times X minus. This is X minus. Okay? All over HX. Because it doesn't matter what that anion is. It's not going to, once we know the Ka or whatever. So, if I do my HX, H plus X minus, and I'm starting with what concentration? 0.085, 0 and 0. What's my change going to be? How do I know what my change is? Because again, if I got to find Ka, I have to be able to know all these. What is pH? What's this telling me?
you can find the H plus concentration.
I would, and that's going to be at equilibrium. So you remember in equilibrium problems, you can be given an initial concentration and then one of the concentrations at equilibrium, and then from that figure out what X is. This is that type of problem. The percent dissociated is exactly like the other type of problem. So we're not learning any kind of new equilibrium problems, we're just applying it to acids and bases. Okay? That's the point that I'm trying to say. So whenever you're given the pH, you're given H plus. Okay? Because we can say that 2.68 is equal to the negative log of H plus, or we can say that H plus is always equal to the pH, 10 to the negative pH. So it's equal to 10 to the negative 2.68. So my H plus is equal to
2.09.
okay? So now I know this is 2.09, so this is going to be at equilibrium 2.09 times 10 to the minus third. So this is going to be minus 2.09 times 10 to the minus third. Did somebody do 0.085 minus 2.09 times 10 to the minus third? .083 molar. So now my Ka is going to be 2.09 times 10 to the minus third squared divided by 0.083. Ten to the what? Okay. All right. What you need to realize, you're not learning any new equilibrium problems. But we just took the test on it. By the way, remember there's the retest today during JAC. Okay? Hopefully you studied. When we were doing equilibrium problems, we either given all of the concentrations directly, which they're not doing really with acids and bases on this one. They're not just going to give you, well, actually that's what it is when they say, you know, what's the pH of a point something solution, you know, OH minus solution or whatever. They gave you finding K when they give you an initial concentration and one of your equilibrium concentrations. Well, the way they do that with acids and bases, they tell you what the pH is. That tells me my equilibrium concentration of this one, and therefore I can figure everything else out. And then the other one was a percent ionized, a percent reactive. And that's how you get your change, and that's what the previous problem that we just did was. So these acid-base calculating Ka or given Ka and calculating H+, they're exactly the same as the previous unit, equilibrium. We're just applying it now to acids and bases. Instead of saying Kc, we're saying Ka or Kb. So don't think that, oh my God, we're just doing everything also. It's really the exact same thing, just with different words. Hopefully you can begin to see that. Okay? All right, take the last 10 minutes and see if you can do the last two problems, next two problems in the notes. But this is for a base. So when you solve for x on this one, what's x going to equal? The OH, not the H+. So what do you have to find first? POH, and then subtract from 14. It's going to be page 15 and 16. See, we're almost done. Only got to go to 22. So your answers are on the sheet, so you can kind of double check it, and I'll come help you if you need help. Yeah. Yeah.
Huh?